25 minutes.
So it's 25 plus 5.
Yeah, 25 plus 5. So the first talk by Koroteev and 3D quivers and integrability.
Okay, thanks. So I'd like to thank the organizers for this great conference. And my talk today will be related to some of the talks we heard earlier today and yesterday. So to Vasily's talk and talk by Kevin Costello. So we'll be talking about, oh, now it's not on. OK, whatever. So so we'll be talking about three-dimensional quiver theories and integrable systems which are related to whatever. Yeah. It's off. I need to turn it off. Just going to use the hard copy. Right. So we're going to start with some motivation. So why would we consider three-dimensional theories? I just need to press harder. Yeah, and it's a bit faint, but it's fine. So anyway, so we'll start with the three-dimensional theories with n equals 2 supersymmetry. And these theories, they possess some interesting features which are not observed in, say, four-dimensional n equals 2 theories. So for example, if you just start with a three-dimensional theory, its masses and couplings, they're real. And you don't have a power of holomorphy to make some strong non-perturbative predictions. But still, if you compactify the theory in a circle and the coupling constants become and mass parameters becomes complexified, you still have this power of holomorphy. Now, Chern-Simons coupling appear, which make the theory more interesting, and they'll be important to computing the non-perturbative data. And the chiral ring of the theory now includes so-called monopole operators, which can be thought of four-dimensional line operators when you reduce one dimension down. Then, if we start from n equals 2 supersymmetry, then theories with such supersymmetry give rise to interesting superconformal field theories in the IR. So we're going to study some n equals 2 deformations of those. So if you're familiar with the work by Garrett and Witten, that will be the n equals 2 star version, in some sense, of the story. Also, mirror symmetry on 3 dimensions is extremely manifest. It simply interchanges Coulomb branch and a Higgs branch. So if you compute something on the Higgs branch, which is relatively easy, you can make strong predictions towards the Coulomb branch computation. And of course, all the powerful methods of string and field theory, like localization, they're also available in 3 dimensions. So we'll take advantage of those. Now, second part of the title, so why integrability? So interesting results by Nekrasov and Shetashvili based on some works by many people before is that so they draw a correspondence between the chiral ring of n equals 2 of observables of n equals 2 gauge theories and conserved charges in the integrable systems or many-body dynamical systems. And in particular, what is important that the supersymmetric vacua of n equals 2 theories, they are in one-to-one correspondence between the solutions of some equations of these integral models, which are sometimes called beta equations. So we can use protected quantities of n equals 2 theories, like vacuum expectation values of BPS operators, to try to understand the most generic approach to integrable systems. And it's nice because connection to integrability tells you how generic your approach is if you are able to cover big families of those models. So we'll be looking at mirror symmetries and Seiberg dualities and find their analogs on the integrability side. So we'll be working with 3 main quantities, which have been discussed in this conference already. So mostly we'll focus on the moduli spaces of supersymmetric vacuum and its inequivalent quantizations. So the superconformal index, which is the partition function on S2 cross S1, and the partition function on the squashed 3-sphere, which was mentioned in Daniel's talk yesterday. So another slide which clarifies things a bit. So Vasily yesterday was talking about a slightly different story, and my talk today will be complementary to what Vasily has said yesterday. So we'll be focusing on so-called low-dimensional or compact version of the gauge beta dictionary. So we'll be looking at the SUSY vacua of 2-dimensional, 3-dimensional, 4-dimensional theories and their compactification on the circles and tori. And that will give us some spin chains with compact symmetry group. And the number of beta roots, number of solutions of those equations will always be finite. Whereas in Vasily's talk yesterday, what he had some, say, 4-dimensional n equals 2 supersymmetry theory with matter, and its Seiberg-Witten curve was related to the classical spectral curve of the integrable system. So for if you take theory with fundamental matter, you're going to get XXX chain. Only now it will be SLN chain, not SU2 chain, and a bunch of different modifications in 5-dimensional and 6-dimensional. So we'll be looking only on the upper part today. Now,
you were saying that the two parts are not related?
Not in a naive way, not that I know. Yeah. They have different brain constructions. Yeah. And yes, as Vasily commented yesterday, so if you look at the 5-dimensional prepotential, it contains its perturbative part contains the 3-dimensional twisted effective superpotential. So it kind of one story is embedded to the other, but it's slightly non-trivial. Right. So first we start with the 3-dimensional equals 2 theories and their Quiver versions. Then we look at the BPS boundary conditions of a 4-dimensional theory, and how to get 3-dimensional theory from there, and how the interplay between 1 and 2 will give us more nice symmetry, dualities between the theory. So in 3 dimensions, so we're going to study supersymmetric mass deformations of n equals 4 superconformal field theories, which preserves n equals 2 subalgebra, n equals 2 3D subalgebra. So its R symmetry is the SU2C cross SU2H. C and H stand for Coulomb and Higgs. The flavor symmetry is again a product of two groups, and so these flavor symmetries they act on the canonical mass deformations of the theory, which you can introduce by turning on some waves of the background gauge multiplets, which are coupled to the flavor symmetry. So on the Coulomb branch, these multiplets are called Fi terms, and on the Higgs branch, we call them masses or real masses. The n equals 2 subalgebra of the n equals 4, we call it U1R, has the diagonal generator JC plus JH, and the orthogonal part, JC minus JH, we'll talk about in a second. But so let's try to build up a theory. We can turn on another deformation, which breaks the n equals 4 down to n equals 2 by turning on the mass which is conjugate to this U1 epsilon generator, which is orthogonal to the R symmetry. So in this new theory, which we can call n equals 2 star in 3 dimensions, the flavor symmetry is now GH cross GC cross U1 epsilon. And so this U1 epsilon, it acts on the R symmetry. OK. And mirror symmetry in 3 dimensions interchanges Coulomb and Higgs branches like so. So it simply interchanges the two SU2s. Now let's talk about the moduli space of vacuum. So the coordinates are built up, given by the masses, Fi parameters, and epsilon. I call epsilon the twisted mass, which is conjugate to U1 epsilon. So we want to complexify it, as I said in the beginning, by compactifying the theory on a circle. And all this use, they acquire the imaginary part, which is given by the R symmetry Wilson line around the compact direction. So because there's a periodic dependence along the X3, we want to relabel U by eta, which is the exponential version of that, which takes care of the periodicity. So the resultant theory has finite massive supersymmetric vacuum, as we'll see soon, and we'll describe the manifold of those supersymmetric vacuum. So we can define a smooth Lagrangian submanifold in the space of these parameters, which are built again by masses, Fi terms, and epsilon, and their conjugate momentum. So to build up a conjugate variable, we need to start with we need to pick some generating function, which I'll specify in the next slide, and differentiate with respect to it. So there will be some momenta and some coordinates, and with some symplectic form on this phase space. And the function which we conjugate with respect to is the twisted effective superpotential of the 3-dimensional theory. So to get it, you need to integrate out all 3D chiral multiplets. To get W as the function of mass deformations and the gauge theory and the gauge multiplet. So it's effective theory of those. Supersymmetric vacuum are simply the solutions of the extremization of by extremizing W, we get the supersymmetric vacuum. So each chiral field gives you some contribution. I call it L of X. And hyper has this kind of thing. So it has charge plus 1 with respect to epsilon, and charge 1 for the chiral part, and charge minus 1 for the antichiral part with respect to the flavor symmetries. And the vector has twice of those. Now, L is pretty much the logarithm plus the quadratic piece, but I'm not writing the full function here. I'm just using the fact that its derivative, exponential of this derivative is the sign function. So generally, this W looks as follows. You take contribution from all hypermultiples, you integrate out, and all the vector multiples you integrate out, and then plus linear term, which has a phi term times the S times the gauge field. Now, we'll be looking at linear quivers. So this is the quiver, which has color labels, which denote the number of colors for each gauge group, and flavor labels, which denote the number of massive hypermultiplet coupled to each gauge group. Not all quivers will be tractable in our analysis. So we introduced the following quantity delta, which in 4 dimensions, what Vasily mentioned yesterday, is related to the beta function. But for us, it's the R charge of the monopole operators. And for the theory to be good, to have a good IR description, those deltas have to be non-negative at each node. So some quivers do not obey this property. They have positive deltas on each node. But sometimes we can turn positive into negative by doing some Weil reflection in the root space. But sometimes it's not possible. So some theories are really ugly, and there's nothing you can do about this. For example, if you take pure Young-Mills in 3 dimensions without any matter, it doesn't have any vacua. So we'll be looking at theories with sufficiently enough number of hypermultiplets. So let's look at an example. Just take one theory with 2 flavors. That's the superpotential. And if you minimize it, you're going to get this equation for the superpotential for the vacuum. So sigma is the exponential is e to the s. And some people can recognize here the beta equation for the XXZ spin chain, which is the deformation of XXX. Has quantum symmetry property inside it. So the taus are exponentials of the phi terms, and 8 is the exponential of the epsilon. So in terms, tau 2 or tau 1 plays the role of the twist in the integrable system, which correspond to the twisting boundary conditions when you close out the chain. The momenta introduced before can be thought of as follows. So if you just look at you can just compute them and write equations for the vacuum in terms of purely momenta and the coordinates, and the masses. Also, we can see that the mirror symmetry is really manifest here. So if you just take this equation, flip a and a to the minus 1 with the sign, and flip masses in the phi terms, it turns to itself. So it shows that the theory T of U2 is self-mirror, and T of any UN is self-mirror. Now, the non-abelian generalization would be to put n equals 2 as QCD. So we're going to have contributions from many hypermultiplets. We have the gauge group, non-abelian gauge group. So this L of Sn minus Sn prime minus epsilon comes from the vector multiplets. This comes from the hypermultiplets. And the equations becomes more complicated. It's a set of polynomial equations with respect to several variables. So now let's discuss which theories are good, which are bad. So the good ones are if, say, number of flavors is bigger than twice the number of colors. They're bad if it's in between n and 2n, and they're ugly if n is bigger than m. So here we can, again, do some tricks. We can take this theory and then say that its IR physics is given by is dictated pretty much by the good theory plus some sector which decouples. It's indeed true if you check that. So you can find some projection between the vacua of one theory and the other. So it's, in some senses, it's a Seiberg duality. There is some support of this fact that the Higgs branch of this theory is the tangent bundle to the Grassmannian. So there is natural symmetry n to m minus n. And for the ugly theories, there's nothing you can do about it. It just does not exist in the IR as a physical theory. And this just supports what I said, that the good theories and bad theories are different by some contribution from free hypermultiplets, which completely decouple from the sector.
What are parameters? Can you remind what are parameters tau 2, tau 1 in the formula for the
Right, so tau is e to the Fi term, e to the RT, and mu's are for masses and sigmas are. Good. So for the generic quiver, you also have contributions from bifundamentals. So that's why equation becomes longer. There is some annoying sign to the right, which you need to care about, but still it's tractable. So the most generic situation is that you have XXZ spin chain with the symmetry group SUL, which transforms under some representation which involves antisymmetric powers of the fundamental representation of SUL. So you could have several copies of fundamental, then several copies of the second antisymmetric power of the fundamental, and so on and so forth. So again, the good quivers, they belong to positive file chambers for the representation R. And I'm not going to talk about it, but you can engineer this chain which lives in this representation by starting with the fundamental guys and then doing some alignments of the mass parameters. Like, say, if you align all the masses in such a string, so you have one mass m plus I minus 1 over epsilon 2, and then this is by 1 bigger, this is by 1 bigger, and again, is a multiple of epsilon. Then what you do effectively, you transpose those, you move those guys into the antisymmetric sector, so they become coupled to the next Dinky node in your diagram. Right, so just to summarize the first part, so you have the 3D mirror symmetry, which interchanges SU2 factors of the R symmetry of the theory, and then it also interchanges Coulomb and Higgs branches. On the level of the modular spaces of aqua, it interchanges the mass deformations of I terms and masses, flips the sign of epsilon, and interchanges the conjugate momenta. And on the level of spin chains, if you just interpret this equation as just looking at the corresponding spin chain, it means that you have a spin chain with the SUL spin chain on M sides, and it's dual to another SUM spin chain on L sides, which is known as bispectral duality in the integrable literature. So this sort of extends the NS dictionary by the fact that the mirror symmetry in 3 dimensions extends to bispectral duality between different XXZ chains. Okay, how am I doing with the time?
Another 7 minutes.
Oh,
8.
I thought I started later then. Okay. Good, thank you. Good, so I'm going to skip on some technical steps, like, for example, how to compute the dual quiver. Let me rather give you an examples. So first of all, it has nice brain interpretation using the Hanani-Witten story. So we have the standard NS brains going this way and D5 brains going that way. So X3 is the direction horizontal on the board. And all D3 brains are aligned along the world volume directions in X3. So they are depicted by the blue lines. So this diagram engineered the theory with the following quiver nodes, quiver labels. So that's 4 colors and 6 flavors for the first one, and so on and so forth. So there are, you see, 15 red circles. There are 15 D5 brains. And on the mirror side, that will give you A14, because there's always one more. So SU15 quiver with the following labels. And there's a prescription to compute them using some representation theory I'm going to have to skip. But the basic examples are, of course, if you take, so the first by interrogator in Cyberg, you take SU2 on M sides, it's this diagram here, and that's dual to this quiver with 1, 1, 1, 1, 1, and 1 hypermultiplet at the first node and the last node. And another example which is important here is that there's a self-mirror theory, which is called T of UN. If you mirror it, it flips to itself. So we looked at SU2, but you can do it for any n pretty much as easily as for SU2. Good. So any questions about the first part? I'm going to move to the boundary conditions. Right. So starting from this picture, we can do the following. We can move all D5 brains to the left and all the NS brains to the right, or vice versa. The pictures look different, but essentially they describe this picture and this picture here, they are the same. So they describe the same theory. And but this picture and that picture and that picture, if interpreted in terms of this effective theory which lives on as given by the fundamental string stretched between these branes, is different from that one. So you have different number of D3s, which will give you a different number of colors. So there are some different inequivalent ways to get one four-dimensional theory from three-dimensional to the other. But let's say we stick with the left picture here. So we look at the D5 or the 5 branes, the NS branes and NS5 brane and D5 brane as the domain walls, which separate two regions in the four-dimensional between two regions in the four-dimensional theory. So D3 brane ending on the 5 brane provides some boundary condition for the four-dimensional fields. So and you can see that just to satisfy the supersymmetry, if you impose Neumann boundary conditions on gauge fields, let's say on the one brane, that requires Dirichlet boundary conditions on the fields transforming. Yeah, so you have SU2 cross SU2 and equals 4 theory, and if you impose Dirichlet conditions on one SU2, it will force this Neumann boundary conditions on the other SU2. And then you can deform it by first breaking SU2 to U1 cross U1, and then doing various deformations on the boundary conditions. Like, for example, you could have multiple D3 branes ending on both sides of the 5 branes, and that would change the boundary condition. So, for example, if you have n of L minus n branes on the left and n of R branes on the right, then the Dirichlet boundary conditions would be deformed by adding the num pole, which has this form. So x sub h is the triplet of scalars which transforms on the second SU2. And it would behave as 1 over x3. So it will have first order pole as the brane approaches, as the D3 brane approaches the 5 brane. And there's some representation theory involved. So the corresponding sides of the representation of SU2 will be, anyway, so this is the ansatz for the scalar. So the idea is to look at this picture as the segment which compactifies a four-dimensional theory. So we have some BPS boundary conditions on the right, if you kind of move these branes close to each other and move these branes close to each other, and another BPS boundary conditions on the left. So the four-dimensional theory compactified on such a segment would have L intersect with LR modular space of vacua. So, and then we can expect, because this picture was obtained from the three-dimensional story, that the vacua of three-dimensional theory would coincide with the vacua of the four-dimensional theory compactified on such a segment. Okay, I'm going to skip the localization motivation to get to the point. Good. So because we turn on the n equals 2 star deformation, we should compactify n equals 2 star theory on the segment. First, n equals 2 star theory in an infinite volume has modular space of vacua, which are parameterized by flat connections. So if it's a UN theory, it's parameterized by the space of flat GLN connections on the torus with one simple puncture. And monodromies around the A cycle, the B cycle, and the puncture satisfy this flatness condition. So one comes from the Wilson loops, one comes from the 2 loops, and epsilon comes from the mass of that joint hyper. And you can see again that there is mirror symmetry which acts manifestly on the flatness condition. Right, so the observation that I'm going to make here is that, so first of all, you can reparameterize this condition in a slightly more convenient way, like so. So that U and V are some vectors, so the matrix on the left has rank 1. And if M in a basis where M is diagonal, so it's like Wilson loops has e to the A1, e to the AN entries on the diagonal, the T matrix has the following parameterization, and there are some constraints on those V's. So what you can show is that, yeah, right. So if the trace M is e to the M1 plus e to the M2, then trace of T gives you the vacuum expectation value of the fundamental 2th loop, and trace M gives the fundamental VF for the Wilson loop. And moreover, the matrix T coincides with the so-called Lax matrix of the trigonometric Rusinaz-Schneider model. It's some integrable systems which has been studied in the context of Chern-Simons theory for some while, and here it appears in a slightly different context. Then finally, the diagonalization of the T leads to the XXZ beta ansatz equations. So let me just show it here on the picture. So you have one Lagrangian submanifold L sub mu, which is provided by the boundary conditions of all the three branes on the left, and then the L sub r, which is due to the boundary conditions on the right. So they intersect somewhere, and the loci of the intersection correspond to solutions of the beta-Ansatz equation for XXZ spin chain. So the duality goes this way. You have n equals 2 star AL quiver, and n equals 2 star superangular theory on the segment with VPS boundary conditions. And there is one-to-one duality between the eigenvalues of the monodromies around the cycles and the mass deformations on the left, and the one-to-one correspondence between the labels in the quiver and embeddings of the SU2 R symmetry into the flavor symmetry, which are different from the left and right boundary conditions. Right. So, yeah, so that's pretty much the same table. If you interpret both sides in terms of integral models, you have XXZ chain on the left and the TRS model on the right, and that's how the quantities are related to each other. Most interestingly, this is quantum classical duality. So spin chain on the left is quantum, whereas the model on the right is classical. And we show how the solutions of the spin chain on the left help you to see how the phase space of this integrable system is foliated by different subspaces, and each subspace is decoded by the quiver labels. So if you take quivers with different labels, different color and flavor labels, that would give you different subspaces of the ambient TRS model. Okay, I'm going to stop in a minute or so. There are some limits. If you take XXZ chain and shrink the radius of compactification to 0, you're going to get the Heisenberg model, which we saw earlier today. And if you take the other limit with some rescalings involved, you're going to get the Hitchin system on a sphere, which is also known as Gaden model. And then there's rational Gaden model, which is limit of both. From TRS, you're going to get more familiar models like trigonometric Calogero or rational RS. And from Calogero, you're going to get rational Calogero. So the horizontal arrows, they designate bispectral dualities. Again, different models with different data are dual to each other. So in the big picture of dualities, we covered only the square. And what remains to be done is the elliptic version, which is not yet clear how to do from the gauge theory point of view. And I have to stop and just flash the conclusions. Thank you.
Questions?
So is it physically clear why for mirror symmetry eta goes to -1 over eta? Apart from the fact that you can kind of see that it has to be true.
Well, the minus sign is not clear. Minus sign is just some. The inversion of eta is pretty much switching the sign of the mass. That's clear. It's pretty much interchanging the action of the U1 epsilon. So U1 epsilon was JH minus JC. Now it's that way around. It's JC minus JH. Just negate the action of the R symmetry generator. Yes. It's the double elliptic. So good. So you have this rational trigonometric and elliptic, and you have trigonometric or elliptic dependence on both coordinates and momenta. So the del guy has both elliptic dependence on coordinates and on the momenta.
It's not a
No.
computer.
There's a question there.
How would you explain this duality to someone who's not who doesn't know a lot of supersymmetric H3?
Oh, good. So part of this dictionary has been known before, just by mathematicians. So what I'm trying to show today is that from the gauge theory point of view, you can get much more than just some examples. You kind of can systematize the dictionary.
I mean, are you going to emphasize the spin chain aspect or the three manifold?
The three manifold aspect, which is the generic approach to the spin chains and stuff.
Why did you consider this particular epsilon information?
Oh, it's pretty much the only one you can turn on to preserve the n equals 2 subalgebra. It has to commute with the U1R. Yeah. Okay.